Welcome, everybody, and happy Tuesday. I am so glad that you are joining us today as we start our day 2 of our final week. I'm really sad that we're going to be ending our time together here in just a few more days, but this is our final push for the AP Calculus BC exam. This is our AP exam prep week. Today is a very special day because we're going to be having a special guest, Dr. Stephen Kokoska, here to talk to us about some common errors and exam tips, as well as throughout the lesson today, we're going to be debriefing the FRQ, the free response problem number 2 that we did yesterday on the air. So if you worked out that problem number 2 with us during that time situation, you might remember we didn't have a chance during the lesson to go over that and share some answers and share some tips with you. So we're going to be doing that today throughout the presentation with our guest speaker today. So as always, if you look underneath the video, you're going to see some hyperlinks there, and you're going to see our Dropbox, which will have all of the materials for today and every day in there. You'll also probably see a whole bunch of extra links underneath there that the College Board has provided. Those are some really helpful links, and Tony will actually be talking about a few of those links here on a couple slides. So speaking of Tony, I am joined with my good friend, right? A lot of people say my good friend on the air, but they don't even know each other. But Tony and I do know each other. We've known each other for years, and we're really good friends. We live pretty close together. So Tony is a good friend, a great calculus teacher from Avon, Indiana, nearby me, and he's joining me as always. And we have, I mentioned, our mystery guest, which I already announced his name, but we'll be introducing him here in a second. So before we jump into the presentation today, we do want to go over a couple of important housekeeping items. Some of those things are going to be just items that are important from what we talked about yesterday, as well as the rest of this week, as well as some other exciting information that I know based on the tweets that we've received from many of you that you're excited to know and hear about. So Tony's going to share some housekeeping items before we jump into our guest speaker.
Absolutely. Thank you, Brian. And if you feel like navigating some of the hyperlinks that you see in the description or video is a little bit intimidating, we've kind of consolidated it here a little bit, and we've kind of compiled the most important links from those particular documents that you might be interested in checking out. So we certainly encourage you to screen capture or take a photo of these particular links and visit them on your own. The ones that have stars by them are going to be links or discussions or videos that we are going to infuse into our programming the rest of the week. So we certainly feel that you can also look at them on your own and just sort of get a little bit of extra exposure if you're tuning in the rest of the week. But we're going to go into a little bit more detail about those ones that have the stars by them. So we definitely encourage you to spend some of the time before now and your AP exams checking those out. If you did not join us yesterday and you missed the great t-shirt reveal, this is the official 2020, maybe it's now the official infamous 2020 AP Calculus BC YouTube Live t-shirt, but there's the front and the back design. And as we mentioned yesterday, a lucky student and their teacher will receive one at the end of each day. We did not draw the winner for yesterday's shirt. We're going to do that today at the end of the program. And on Friday, we'll have to draw 2 names to take care of both Thursday and Friday's winner. And we'll give details to how we will send out those shirts when we contact you. How to win the shirt? I know you're asking. Well, all you simply have to do is at any time this week, just send a tweet to at PasswaterB at AP Calculus Teacher T. We would like you to AP Calculus Teacher, and we would like you to attach a screenshot of the College Board AP exam practice confirmation. Right? We talked a little bit about that yesterday. Just we want to see that screen that confirms the fact that you've submitted your little practice attachment so that you've gone through that process. You only have to submit once, right? Once you submitted, say yesterday, you're still in the drawing for the rest of the week. And like I said, we're going to choose a winner at random. And here in just a little bit, we're going to give you another way to double your chances at winning a shirt. So stick around here in just a few seconds as we talk about that. Our week ahead. As we already discussed, we have an amazing guest speaker today, former Chief Readers, Dr. Stephen Kokoska, who's going to go through some common errors and misconceptions on the AP Calculus exam. And we hope towards the end to have a little bit of live question and answer with him. And if you do happen to submit a live question via Twitter, we will enter your name twice into that drawing. So think about some questions that you would like to ask Steve Kokoska, and we will try to get them on the air for you. Tomorrow, we're going to discuss the College Board exam portal entry process one more time, giving you an alternative way that you can submit your work and maybe reviewing the ideas that we spoke about yesterday. And then tomorrow is mock exam free response question 1 day. Now remember, we did question 2 yesterday. We're going to do question 1 tomorrow. Question 1 is the longer question, the 25-minute question. Thursday, a little bit more additional mock exam practice to fine-tune some of those topics. And then Friday will be our last-minute tips and our YouTube live recap. And who knows, maybe some tearful goodbyes. Looking a little bit more closely at today with Dr. Kokoska. Again, we're going to talk about the common errors, misconceptions, and he'll give some exam tips. And we would encourage you to send out your questions live via Twitter to Passwater B, AP Calc teacher. We are going to debrief question 2. So as we said, we want to make sure that you have that question handy. If it's not there with you, grab it really quickly, because we are going to be talking through those particular solutions throughout the day. And of course, our t-shirt giveaway at the end. So wow, Brian, that's a full show right there. We could stop right here, and no, we're not going to do that. We have too many great things to do. Brian, why don't you talk a little bit about our special guest today, because I'm excited. He's one of my favorite people in the world of advanced placement calculus, and I know you feel the same.
Yes, and I'm sure Steve will be thrilled to know how much we're pumping him up. Nothing makes a guest speaker feel less intimidated than us telling how awesome he is, but that is not hyperbole. And we know our students are going to appreciate, and teachers appreciate, all of the insight and just really down-to-earth advice and understanding about the exam and exam tips and things like that. So I want to reiterate again, tweet at us, right? At PasswaterB, at AP Calc Teacher. If you're a teacher or a student and have some questions, tweet them, because we're going to get a lot of those on the air with Dr. Kokoska here in a second. So, what can I say about Steve? He's been a great friend of ours. Steve, you might recognize his name because he's been doing some TI office hours. He's got some coming up. We'll announce actually a really cool opportunity, a free opportunity for students to have some more online free practice coming up at the end of the program with Steve and another friend of his through Texas Instruments. Steve also has been a former chief reader for the exam, and he's been a test development committee member. Maybe you recognize Steve as a name on your textbook. He just released recently, a couple years ago, a textbook with Stuart Kokoska, AP Calculus textbook, meant for AP Calculus students, as well as couple editions of some statistics textbooks as well. So he's kind of been all over the place. And to top all of that off, he's still teaching actively at Bloomsburg University, and a world-renowned, I think it's world-renowned, isn't he a world-renowned ranked pickleball player? I believe. Is that right, Tony?
I would call him a world-renowned pickleball player. He sure does play a lot. I do know that.
Yes. So we are so excited to welcome Steve. So Steve, thank you for joining us. Sorry we set the bar so high, but we only did it because we know you will still exceed that. I mentioned in my introduction that you're a former chief reader and a test development committee member. If I was a teacher or a student out there, I wouldn't know what that means exactly. So before you jump into your presentation, could you share just briefly what those two roles are so we can have a better understanding of what that means for the AP exams?
Absolutely. The pickleball bar is way too high. Brian, Tony, look, thank you very much for having me on your show. I'm absolutely delighted to be here. And thanks for all you're doing for the AP Calculus community. And especially to the teachers who are out there, real thank you to all of you for what you're doing under these extreme circumstances. I say this frequently, but I really do mean it. I admire what you do. I am somewhat envious because you have the opportunity to teach our best and brightest. And I think that's just a lot of fun. The chief reader job, well, you know what? It's really a full-time job. Although my provost never understood that, it is indeed a full-time job. The chief reader answers questions, makes decisions almost every single day, mostly about the reading and scoring, but also about silly things like what are we going to serve for break on the mornings of the reading, who should we have as a professional night speaker, that sort of stuff. But in all honesty, my main job is to oversee the scoring of all of the exams, all of the forms, all over the world. It is to ensure good and correct mathematics. It is to ensure consistency across all the questions and across all the forms. And the truth is that the chief reader is sort of the ultimate decision maker in all scoring decisions. So you guys have participated in the reading. If there is a question about how a particular exam is scored, it would go to a table leader, an exam leader, and question leader. Eventually, it might get to the chief reader. I also participated in the development committee, and basically there I was involved in creating the exams, writing the exams, which, by the way, is a 2-year process. It takes roughly 2 years to create an exam. So on the committee, I contributed to the writing, but mostly I was the authority on the committee on scoring. So I would help answer questions like, are there 9 points in this question? If you ask this particular question on the exam, can we score it in a consistent way? So I provided another set of eyes also, and basically contributed to the construction of the exam, and especially the scoring. Quite a process, a wonderful experience for me, met some great people, dedicated, committed teachers like yourselves. So shall we try this? I want to look at some common errors. I'm going to switch a little. I know that you guys have been looking a lot at content. I'm going to switch a little as we get close to the exam, if it's okay. So I have to turn off my video. I'm going to share my screen. I'm going to flip my tablet around here, and I hope you can see that. Is that correct?
Yep, looks good.
All right, fantastic. So what I'm going to try to do is to present to you some common errors, and I've compiled these over the years of all my experience in scoring exams, in presenting as a College Board consultant, and in writing and talking to teachers, talking to students. So this is a list of common errors, and what I've tried to do is to write the common error in red, give you a second or two to recognize what the error is, and then I'm going to elaborate on that a little bit. So this is one of the most common errors that deals with the quotient rule, and you can probably see this one pretty quickly. It is a reversal. Up there in the numerator. And this is a very common error. I'm going to write a little bit down at the bottom, and let's see if we can make this work. So that, of course, we know that if a student needs to take the derivative of a quotient like this, f divided by g, they have to bring the denominator up first, take the derivative of the numerator minus the numerator derivative of the denominator divided by g squared. Now, of course, the reversal in the numerator is a common error, but another common error, and Brian and Tony, I know you guys will remember this, is if this function g down there happens to be a binomial or a polynomial of some form, a very common error is in the denominator, to write something like this. X plus 3 without any parentheses, x plus 3 squared. And that, of course, is ambiguous. And that, as I read it, you know that there is a big emphasis right now on communication, notational fluency. And as I read that expression as it's written, that's x plus 3 squared. It's not the quantity x plus 3 squared. Now, it's possible that that notational error could be corrected later on if we were doing something else with this derivative. But if we were just finding this symbolically, that's wrong. And so what often happens is that parentheses, of course, is missing. Now, it's not just in the quotient rule that applies to a lot of other places, but this is a very common error. And Brian, I think you were going to tie this in with something that you guys did, one of your questions.
Absolutely. And so if you were with us yesterday, students, we shared our first FRQ, our first practice test FRQ. We had a timed simulation to let you practice taking it under a timed constraint, as well as practice the uploading process. And so we told you that we would be going over that question today. So we're not going to be going over this question like all at one time. We're actually going to be introducing it and weaving the different parts of the question from yesterday into Steve's presentation where it kind of fits in. So if you have your test from yesterday, your papers, it's a really good chance to grab those real quick. Maybe you need to pause the video and go grab it if it's not right in front of you. But take a look at your answers. So we're going to have the answers in red, and we're not going to go very in depth on the answers throughout the presentation, unless we might make a couple of comments on some more challenging ones. But we really want to use this as an opportunity for you to see what the solutions were, what the answers were, but also so that way Steve can elaborate on his presentation on how that might look. So Steve, this was our first part A from yesterday. It was a quotient rule. And Steve, this is how I envision it, and maybe you can clarify, but on this exam, with all of the resources and technology and things that students are going to have on this take-home test, the quotient rule might look more like a problem like this, where you couldn't just Google this question because of that f of x in the problem. And so that might be a typical good way the College Board might ask these type of questions. But what would you imagine might be if we were scoring this problem, if it were an AP exam question, some errors and some things that students should look out for based off of what you just shared?
Yeah, a couple common errors. First of all, in your first step in the numerator, a common error would be to reverse the numerator. And a second common error, one that we didn't mention yet, is towards the end of this. Remember that you don't have to simplify a numerical result. So your first step there, where you have the f of 3 quantity squared in the denominator, so move one to the right, there you go, the f of 3 squared in the denominator, that step right there, that's not a final answer if we need a numerical answer, because the student would be required to pull that f of 3 from the table. But the next step in which that f of 3 is taken from the table, that is a final numerical answer and does not have to be simplified. And so if a student went further and instead of writing, for example, 21 over 8, they wrote 22 over 8, even though they've done everything else correctly, they would lose a point somewhere. So that's a very good question, and I agree with you, Brian, that this question would be a good one because students would not generally be able to go to a CAS system and get an answer. This would require them to do this analytically, use proper notation, and the right concepts. So I agree completely. This is a good example.
Perfect. And I think, Steve, also, this would be a good example. You might remember this when a couple years back we had that quotient rule problem where it was F and G actually in the quotient,
Yeah.
but they had it flipped. So a lot of times textbooks will have F on top and G on bottom, and students were just blindly writing the quotient rule they memorized and not applying it to the problem. And they ended up reversing the letters and having that F on bottom. If students aren't applying the quotient rule to this problem, they might just go to some blanket formula where the F is normally on top on their textbook or normally on top in their notes, and somehow could create some confusion with that if they're not thinking about applying the rules to each individual problem.
Yeah, absolutely. Excellent point. Yeah, excellent point. All right, shall we try the next one?
Please.
Oh, sorry. Should we try this one?
Yeah, great.
Okay, good. Let's take a look at this one. So this is a very common error that involves the chain rule. If we have a composition of functions, f of g of x, and we want the derivative, a very common error here is, and you can probably see this one already, is to forget to take the derivative of the inner function. So the correct answer here, of course, is the derivative of capital F is f prime of g of x times g prime of x. And I'm going to write just a little bit down here, Brian, before I pass this over to you. So here's a very common example that one might use if I want the derivative of the sine of x squared. The student has to recognize that that is indeed a composition of functions. And at least the way that I teach this is they have to think about what is the inner function and what is the outer function. And so if I want the derivative of capital F, I start at the outside taking derivatives. The derivative of the sine is the cosine. I leave the inner function alone, and I multiply by the derivative of the inner function. You guys, I know, remember a couple of years ago, there was a function, I'm going to call it capital F, but I don't remember what its symbol was. There was a very easy function on the exam. It was simply e to the 4x. Mm-hmm. And I apologize, I don't remember the context of this, but part of this problem required students to take the derivative of this function. And so in order to take the derivative of capital F here, they needed to take the derivative of the outer function, which is just e to the u, e to the 4x, times the derivative of 4. And one of the most common errors, I'd say almost a quarter of the students forgot to take the derivative of that inner function and multiply by 4. So the chain rule is a very important concept in AP Calculus. In the past, we've always awarded 2 points on the free response portion of the exam for a chain rule error. So if I had to make a stab, I would say there's going to be a chain rule portion of a question somewhere. and also the fundamental theorem of calculus, but certainly a question that involves the chain rule. Now, I think you had something about Monday's FRQ here too. Is that correct, Brian?
Mhm. Yeah, I think Tony is
Okay.
going to share. We're going to jump to part D. Is that right, Tony?
Yes, I believe part D illustrates that particular concept best on the actual FRQ2 that you had. So you might want to flip to part D there. And in this problem, we were still working off the table, and we had defined h of x to be this definite integral from 1 to x squared of f of t. Your job was to find h prime of x, h double prime of x, and then explain why h could not have that relative extrema or a point of inflection at 3. So in this first part, you see that we are knee deep in a fundamental theorem of calculus here, right? Whether you call it part 1, part 2, but we're talking about inserting that x squared in for that value of t. But as we said, that all important chain rule step is of necessity for this particular problem, and certainly readers are going to be looking for that. So what we're going to do is multiply by the derivative of that x squared, which of course is 2x. That would likely earn a point. You've found your h prime of x. Now for h double prime, we've got a special little treat here, because now that we've already tested you on the quotient rule, we've tested you on the chain rule, we get to see how well you know the product rule in this case, because we do have a product, 2x multiplied by the f of x squared. So you can see how we've carried that out pretty effectively here with the derivative of our first term times our second plus our second term. And then once again, the derivative of that second term does produce yet another chain rule. And at that point, you can choose to simplify this, but you don't really have to. You could rearrange some things, multiply the two x's together, but this is still going to be serviceable. This is going to be acceptable. And at this point, you just springboard into actually evaluating both of these at the value of 3. You'll be pulling some values from the table. That's going to be very important. And you'll notice that you'll get results of 12 and negative 32. But the important thing is to make the connection that neither of those numbers is equal to 0, nor are they undefined. So what that means is that you can't possibly have a relative extremum or a point of inflection for your graph of h.
And Steve, this problem might actually look similar, because one of your earlier office hours from Texas Instruments had a similar problem like this that inspired this. So if students and teachers like this problem, especially that double product rule that kind of slipped it there at the end, those are the kind of problems that Steve will be sharing on these office hours.
Yeah, I think this is an excellent problem. Not only does it test the fundamental theorem of calculus, but there are some other concepts in here about how to take a derivative. There's some concepts in here about what happens when you have a relative extremum or a point of inflection. So this is a great comprehensive problem. Yeah, very good. All right, I'm going to try another one. Here we go. So this one has to do with particle motion. And a very common error is that total distance traveled is the same as displacement. So of course that's not true. And displacement we would find by taking the definite integral from a to b of the velocity function. This is how much the particle has moved to the left or to the right over a time period. The total distance traveled is the integral from a to b of the speed, or the absolute value of the velocity. One question I'd like to ask here, I don't know if we can get answers quickly over Twitter or not, Brian or Tony, but one question I'd like to ask is, you know, this kind of a question where we ask the student to find the total distance travel in past years has been on a calculator active portion of the exam. Mm-hmm. Now, since students have access to calculators for all of this exam, I'm wondering if that kind of a problem could be asked, where the student would have to do it analytically. So a question I might ask is, how do you solve this kind of a problem? You have to take the absolute value as the integrand. How do you solve that analytically? So maybe you could think a little bit about that. Maybe you could send in an answer to Brian or Tony. And while they're looking at that, I'll go on to the next one, which has to do with particle motion also.
Great.
So this is a common error, and that is the particle changes direction wherever the velocity is 0. A common question in particle motion problems is, for example, here's the position function, or here's the velocity function, or even the acceleration function. Find out where the particle changes direction over a certain time period. And students will often find where the velocity is 0 and say, well, okay, that's where it changes direction. And of course, that's not true. we have to take a look and make sure that the velocity does indeed change from positive to negative or from negative to positive across that time, across that value, across that number. That, by the way, sort of begs the question about sign charts. I know you want to ask me about that, Tony, and I'll get to that in a minute. So hold that aside if you would. And since we're talking about particle motion, here's another one. Generally, in these particle motion problems, we've seen questions about the speed of the particle, and a question like, is the speed of the particle increasing or decreasing at time t? Well, remember that the speed of the particle is the absolute value of the velocity. And how do you know whether or not the speed, for example, is increasing? I'm going to try to write a little bit down at the bottom here. This leads into another, I think, common error. Let's suppose you're asked, is the speed of the particle increasing at a particular time? Well, in order to answer that question, I'm going to take a look at A of t, I should probably call this t1, and V of t1. I want to know what's happening at that time t1. And what we need to know is, are these values, do they have the same sign? Are they both negative or are they both positive? If they have the same sign, then the particle is speeding up. If they have different signs, then the speed of the particle is decreasing. Now I'm going to add in here, this is just an example. If you get a question like this, in general, the question does not ask for these values specifically. And so a test-taking tip is don't write them down. Because if you calculate them, you must calculate and report them correctly. In a calculator active problem, they must be reported to 3 decimal places correctly. So if you're asked about the speed of the particle, just calculate these values, find them, but don't necessarily report them unless they're asked for. And one more thing down at the bottom, since this is a calculator active question, and this is one thing that I learned, I thought this was very clever. You can actually use technology to take a look at the derivative with respect to t of the absolute value of v of t. And if that turns out to be positive, then the speed is increasing. If it turns out to be negative, the speed is decreasing. That is another way to answer this question using technology, which I think is pretty cool.
Perfect.
Okay, can I go to the next one, or did you guys have something to weave into yet? I apologize.
Well, no, you're doing a great job, Steve. Actually, we have a whole bunch of Twitter questions, so I don't want to interrupt the flow of your presentation, but do you mind if we pause just for a couple of minutes just to let you answer a couple of the questions that are coming in that I think you're uniquely positioned to answer?
All right. Well, let's do one more.
Sure.
Let's do one more, and then we'll kind of transition into looking at critical numbers and points of inflection.
Perfect.
And that sort of thing. So let me do one more.
Okay.
Because I know you asked me about this one. I think this is a good one too. This is an error here. So one common error is that the value of C that satisfies the conclusion of the mean value theorem is always the midpoint of this interval. Now that sounds kind of silly to those of you who have been studying this for a while. But I'm telling you, my years of experience, this is a common error. That the students reflexively decide that that value of C must be the midpoint of that interval. And of course, that's not true. So the value of C that satisfies the conclusion of the MVT could be the midpoint, but not necessarily. Okay, this value of C is just a value, so that the derivative at that value is the same as the slope of the secant line. Now, the way that I've drawn this picture on the left-hand side here, it sort of looks like it's in the middle, but of course it doesn't have to be. The slope of this tangent line right here is the same as the slope of that secant line. And on the right-hand side, I've drawn an example of, it might be that there are 2 such values of C in that interval A to B. Now, I didn't write this down as a common error, but Brian reminded me, or Tony reminded me, that another common problem here, common issue in these mean value theorem problems, is that students need to verify the conditions or the assumptions that guarantee that there is such a value. So I'm just going to write that down underneath here, is to make sure that you state the conditions. Make sure, for example, in this mean value theorem problem, or if that you state that you check that indeed the function is continuous on the closed interval, that is differentiable on the open interval. Therefore, there is a value C that satisfies this condition. So that's maybe a good segue. Do you want to take a look at some of those questions?
Sure, and I'll ask you some, and then we'll get right back to the presentation because there's too many really good things that Steve's going to be sharing. So I just want to take a couple of minutes, because otherwise we're going to have hundreds of questions that we're not going to be able to get to. So I'm going to do a little bit of maybe some rapid fire with you, and then you could give your feedback. And also, I'll preface this, and I know you would preface this as well. This is not an official College Board response. This is not
Correct.
College Board's answer. So this is the insight and thoughts of a former chief reader and development committee person who's got way more experience than maybe anybody I know in the country about the AP exam. So it's good insights, but don't take this as a College Board statement, right? So one of the questions was, are the cutoff scores for what it takes to earn a 3, 4, and 5, are those predetermined before the exam?
No.
And how are those generally? Is there an easy way or a short way to explain without going into super detail about how those are determined?
They are equated with previous year's exams up to a point. So there is some sort of norm. Maybe the last 3 or 4 years are the norm, and the scores on the exams are in some way equated with all of those scores, so that a 5 last year is equivalent to a 5 this year.
Perfect. This one, you've answered part of it, but there's a second part I think it's a good question is from Tim. How much should we simplify our answers? And I think you kind of mentioned that, but the second part is, how much work do we need to show for each question?
Well, okay, so a final numerical answer does not need to be simplified, that's for sure. So my kind of pat answer to that one is, if you have to evaluate a definite integral, and the answer, for example, is 0 cubed divided by 3 plus the sine of 0 plus 1, you don't have to simplify that. That is a numerical answer. You don't have to simplify it.
Perfect.
Okay? How much do you write? How much do you give? Look, you need to be succinct, but you can't just write a bald answer. Your solution, your student's solution, must follow, I believe, in a very logical way. I need to be able to follow the solution. And this brings up a good point too, by the way, Brian. I don't think I have this listed, but I'm sure you guys have probably talked about this issue of linkage, which is don't connect things that aren't equal with equal signs. That's sort of this train of thought error. Don't just connect things with equal signs. Do them in a logical, step-by-step method, prescriptive method, if possible.
Yeah, we'll see an example of that with one of the questions from yesterday's FRQ that Tony will share on the average value. With those average value problems, we see a lot of linkage errors where students try to sneak in that fraction at the end without a linkage error. So 2 more quick questions, Stephen. We'll let you continue, and we'll stop again later to ask more questions because we have so many good questions coming in. So my question for Steve from Caitlin is, what are the skills that the AP Calc test is looking for, and what's a good way to practice that skill?
Boy, that's a tough answer. We could spend a whole hour on that. Look, I think right now the College Board is testing conceptual ideas. They want to make sure that the student has a good conceptual understanding with some analytical skills. Now, look, the truth is that colleges right now have been slow to follow the AP Calculus lead. And so we do a little bit more. We focus a little bit more on manipulative skills. But the AP Calculus exam, I believe, tests conceptual understanding. Do you understand the big picture? I think you will see, if you go back and look at past exams, points have been awarded for conceptual understanding. For example, does a student know they need to set f prime of x equal to 0 and solve that?
Perfect. And then one last question from Faith about the scoring of the exams. How does the scoring work? Meaning, do you only gain points for the work that you get right, or do you lose points if something's wrong? Is it better to try continuing a problem if you don't know it, or just stop when you're stuck?
Look, in general, we don't take away points. We like to think of reading a student's paper and having them earn points. There are certainly cases where a student can lose some points. The standard one we might have just talked about, where the final answer is numerical. A student has it correct, but goes on to say something else and makes a mistake, and we have to take one off. Sometimes a student says too much. For example, they may report the correct answer and have earned the point, but go on to tell us something that is patently false, and we may be forced to take off a point. So the student shouldn't say too much. They should be succinct. They should write as much as possible to support the solution. I hope that helped a little bit, Brian.
I think this is excellent, and there's a lot more questions that have come in, and we'll hopefully have time at the end to do more, but some of these I know are going to apply specifically to some of the slides that you're showing today, and so we might sneak in a question here or there during your presentation that applies to the area that you're going to be addressing. So we'll let you continue with this, and we'll continue to weave in some of these questions as we go.
Okay, thanks, Brian. So the next couple of common errors all deal with the analysis of functions, I believe, and I think this has been a very common sort of a question on the AP FRQs. So I think, I'm going to make a guess, I think there's going to be something to do with the analysis of functions. So a common error is that if C is a critical number, then F must have a local max or a local min at C, and of course, that's not true. The way that I think about this, that if C is a critical number, then it is a candidate. I'm going to write just a little bit down at the bottom here if I can. So if I'm looking for local maxes and local mins, I have to find places where the derivative is 0. I have to find places where the derivative does not exist. Those are candidates for local extreme values. I apologize. I wish we had the time here to talk about sign charts and the use of sign charts. And I wish we had the time to talk about endpoints, but let me just say a couple of things about both of those topics. First, look, there is no prohibition against sign charts. I use sign charts in my class. A student can use a sign chart, but the point is that it is not sufficient justification for whether or not a function has a local max or min at a value. So a student is free to use a sign chart, but then they must provide some sort of written justification, or the way that I think about it, an interpretation of that sign chart. Another issue here has to do with endpoints. Since we're talking about critical numbers, we might talk about where a function is increasing or decreasing. So for example, I often get this question, I'm just making this up, is it okay to write, for example, that a function is increasing on that interval 0 to 2 and decreasing on this interval 2 to infinity? In other words, can I include that 2 in both of those intervals? And the answer is yes, you can. And the reason is because of the definition of increasing and decreasing. Now, again, we could spend a lot of time talking about that. That's the correct way to write it, as long as there's no contradiction with the function. But the truth is that when we grade these, we don't look at the endpoints, whether or not you've included them, whether a student has included the endpoint or not. So the point is that a student could write them as open or closed, so long as there is no contradiction. For example, a student cannot write something like this. They cannot write 0 to 10 closed, where the function is not defined at 10. And a student could not write 0 to infinity closed. That would be really bad also. Okay, so another common error here in dealing with the analysis of functions is if f double prime of a is equal to 0 or doesn't exist, then f has an inflection point at a. Well, this is very similar. This is a candidate for an inflection point. And so once again, a student can use a sign chart. We've seen lots of examples on FRQs where a student has the first derivative graphed, and they could look at where that is increasing and then changes to decreasing. So again, this is a candidate. The student must justify why they have a point of inflection, why f has a point of inflection. And I have a note here about endpoints. We're not going to worry about the endpoints here, whether or not the interval is open or closed. In my opinion, these should always be open, but we're not going to worry about that when we grade this, so long as there is no contradiction. Cool. Brian, I apologize. Did I have this slide on there? Can I say something about this one? Is this okay?
Absolutely, Steve.
Okay, good, very good. This is a cool error here. This is very subtle, but this is a common error. If f prime of x is greater than 0 for x less than c, and it's less than 0 for x greater than c, then f of c must be an absolute maximum value of f. This is very subtle, and the missing word in here is for all. And for all. This is a common error when we ask students to find absolute extreme values. The way that this is presented, it is a local argument, and I caution you about this. And so I'm going to write down a little bit here at the bottom. How do you justify absolute extreme values? Well, look, when I was the chief reader, Tony and Brian know this, whenever there was a question on the FRQs that involved an absolute extreme value, I used the table of values method, the candidates method. I want students to create a table of values, and in that table of values, I want the endpoints of the closed interval, and I want all the critical values, and I want the student to evaluate the function at all of those points, pick out where is the smallest value, where's the largest value. Look, for my money, that's a very prescriptive way to solve this kind of a problem, and it's the way that I recommend students to solve these kind of problems on the exam. Now, you're right, there is a little bit of a drawback. The table of values is the justification for the extreme max or extreme value. But anything you write in that table must be correct. So that means if you evaluate the function at a candidate, for example, at a critical point, and you happen to evaluate it incorrect, even if it's not the absolute max or min, the student would lose that justification point. Now, even said that, I still believe that this is the best way to justify an absolute max or min, get a table of values. Now, when a student does that, one more word here, make sure that the student actually answers the question. Is it a question asking for, well, where's the x coordinate for the absolute max? Or is it asking for the actual absolute maximum value? Now, you're right. Again, the student can use a modified first derivative test here, but I'm telling you that most students are not successful in doing that. They usually make this error up here of the local versus the global argument, so that the table of values argument is usually the best. Brian, I think you had something. Did you have something here you wanted to add, or should I go to L'Hopital?
I think you can go to L'Hopital. I think you hit it right there, which is the idea of using a table of values for that extreme value.
Okay, fantastic. Okay, in applying L'Hopital's rule, a common error here is that students take the derivative of the quotient using the quotient rule. Well, we know that that's very wrong. We know that when we apply L'Hopital's rule, we want to take the derivative of the numerator, derivative of the denominator separately. I'm going to write a little bit down at the bottom because there is an issue here about notation that came up last year, which I disagree with, but I want to tell you what happened and where we are with this. So last year, we had a problem, or the year before, where the function f was going to 0 and the function g was going to 0 as x goes to a. In my class, my students would try direct substitution, and they would write equals 0 over 0, and they would say, you know what, that's an indication to me that I need to do something. And so I would probably go on to use L'Hopital, or even before L'Hopital, I might be able to use an algebraic argument, or maybe even a geometric argument. I'm telling you, don't write this down. I'm telling you that that notation was not accepted last year. That notation was not accepted as an indication that you need to use L'Hopital. What do you need to do? Well, you need to separately check the limit of f of x and indicate that that's going to 0, separately check the limit of g of x, that that's going to 0. Now, I'm still arguing with Julie about this, and this may change. This is subject to the chief reader's discretion. This may change, but I'm telling you that last year, this was not accepted, but there was some little differences in this that were, which just seems strange. For example, If a student wrote an arrow like that and said, that's going to 0, that's going to 0, that was an indication that you need to use L'Hopital, which seems sort of strange to me. There were a couple of other little distinctions here where it was okay. The safest bet right now, my recommendation, do that. Make sure you check the numerator, make sure you check the denominator separately, and then you can apply L'Hopital's rule. One extra little thing here, one sort of common error embedded in all of this is, remember to carry along this limit symbol. Don't get rid of that limit, darn it, until you actually execute the limit, until you actually find the limit. Cool. All right, I've got another one here that deals with the substitution rule. Remember that when you use the substitution rule, some students leave the antiderivative in terms of u and don't bring it back into the x world. So I'm going to write a little bit down below here. I'm going to try an actual example. I'm going to write 0 to 1 of x times x squared plus 1, or plus 7, I think, all of that raised to the 9th power. Let's suppose a student wants to find that definite integral. Now, look, I understand that some students are really good at this, and some can actually look at that and know what the antiderivative is right off the bat. But I'm still going to recommend to you that you write things out. This is a good tie-in to a question from a couple of minutes ago. Make sure you demonstrate all of your steps. And one good reason for that is so that we can award partial credit. So here's the way that I do this. I define u to be equal to x squared plus 7. I find du, that's equal to 2x dx. And through all of this, I hope to demonstrate what the couple of other common errors are. The way that I do this is I actually solve for dx. So I find du divided by 2x is equal to dx. And since this is a definite integral, I've got to drag along, I've got to drag along the bounds. So I've got to find u of 0, which turns out to be 7 in this case, u of 1, which turns out to be 8. So, okay, I got to bring everything from the x world into the u world. So this becomes the definite integral from 7 to 8. I'm going to leave my x alone. X squared plus 7 is u, that's u to the 9th. Dx, let's see, is a du divided by 2x. Okay, I'm going to stop there for a second. That step is fine. That is an intermediate step. That's sort of the bridge. I'm walking across this bridge from the x world to the u world. My next step is I'm going to cancel out the x's. I'm going to bring the 2 through the integral sign. But the important thing I think here is that these bounds. If you bring everything from the x world into the u world, you've got to drag along the bounds. A common error here is to leave this as 1 and to leave this as 0. Now, some of you are thinking, well, wait a minute, what if I write x equals 0 and x equal 1? Can you do that? Yes, you can. But my response is not to be flippant. Why would you want to do that? Look, you're going to find the definite integral here in terms of u. You're eventually going to have to substitute x into your expression for u. You might as well do it right away and use the correct bounds. It seems silly to me to integrate with respect to u, bring everything back into the x world and use the x bounds. We've actually simplified this a little by bringing it into the u world, use the bounds in the u world. Okay? Cool.
Excellent. And Steve, right here, I want to share one of the problems from yesterday's exam real quick, just real briefly, so we can continue. So this is our question BC2 from yesterday again. This was part C, and it kind of relates to this idea of definite integrals. It's not a U substitution problem, but on the BC exam, it's possible we could see one of those other integration techniques. And so this one asks students to evaluate the integral from 3 to 8 of x times f double prime of x dx. And so it turns out this one is going to be solved by using integration by parts. And I'd love your advice on this, Steve, because I'm always, worried about some of these linkage errors, like you mentioned, saying things that aren't technically correct, even though a lot of students will fix it later on. They've written something down that's not quite right in that step. And I think with integration by parts, because of those limits of integration, and they have to do part of the integration and they have another integral to deal with, sometimes they get confused on do they put that little evaluation bar there, or what happens if they don't put it there and then have the 3 and the 8 there. So I went ahead and just did the indefinite integral as my work, and then I plugged in the values from 3 to 8. And students, you can see the work there, and we're not going to spend a lot of time discussing the solution to this, and maybe take a screenshot of it so you can see the work. But notationally, Steve, what kind of pitfalls might a student have on something like this, where they have to do integration by parts with those definite integrals?
Yeah, this is an excellent example, I think, to demonstrate not only notation, but also to show all of your work, Brian. This is a great example. Your second line down is the one that I really liked. I generally use the brackets or the square braces to indicate that entire function, that entire expression inside must be evaluated at both the upper bound and the lower bound. We need to subtract. I think that's the way that I would do this. I don't know personally whether or not I would do a separate integration by parts. I might have my U and DD identified and then go directly to your line 2. But you know what? Good advice to students is write that out, because you know what? You might get some partial credit for it, and I can see exactly what you're doing.
Mm-hmm. And then we're able to stop correctly, right about here. Once we have values plugged in, we can leave it there, and then not worry about trying to do arithmetic, especially on a timed test where maybe we're feeling some pressure with time.
Yeah, absolutely. Good point, Brian. Yep.
Awesome.
Okay.
I'll let you jump back into it there.
Okay. I apologize, Brian. We're going a little long here, but I'll keep going until you stop me, okay?
Sure.
This one I can do very quickly. This one has to do with volumes by washers. I believe this is on the BC exam. This may seem silly, but this is a very common error where students will take the difference of the outer radius and the inner radius and square that. And you and I know that that is incorrect. The volume here is, in general, the definite integral of pi times the cross-sectional area. And we know that the way that we derive this formula is by taking a look at cross-sections, which are circles, and we end up with this washer method. It is the outer radius squared minus the inner radius squared. So that's just a common error. I don't have too much to add there. Be very careful about notation. That's a tough one.
Mm-hmm.
This one we see often. You know, this is something that, believe it or not, the College Board has been sort of criticized for asking about the average value of a function frequently, but students make this error comment often. The average value of a function over the interval is often one of these two reported values. This expression is really just the average of two values. That's going back to introductory statistics. And this one, of course, is the average rate of change of the function over the interval a to b. And either one of those is correct, of course. The average value of a function over this interval involves a definite integral, and it is indeed that expression. I think, Brian, Tony, we've talked about this a little bit. I can see where the College Board could weave in this average value into a problem, even on the AD exam, by not mentioning this as average value, but a table of values somewhere. This might appear.
Sure. And this is, I think, the last one of the last parts of the FRQ from yesterday that Tony is going to display
Okay,
the
good.
solution for.
Yeah, just really quickly, I believe that this was our part B. So if you're flipping back, you can take a look at your solution to part B. And you see this idea, use the left Riemann sum, and it's so easy for students to become laser focused on that idea, but you want to make sure that you read the entire problem, because you are asked to approximate the average value of that function f of x. So this 1 over b minus a, this 1/8 that's out in, is certainly something that readers are going to look at. And I'll let maybe Steve speak here in a moment to maybe the egregious use of the equal sign here, but it's not great communication to use an equal sign there. Sometimes we'll overlook that, but you want to communicate well, right? If you're writing a paper in your AP Lit class, AP Government, you want to communicate well. And we do the same thing as mathematicians. We want to communicate. Notice how that 1/8 does carry over, and you're just using your traditional approach with your left Riemann sum setup. Really important that you're showing sum of products, as we've talked about. Now, just really quickly,
Right.
let's suppose, what if a student forgot this 1/8? And then all of a sudden they got to the end of this problem and they said, oh, I need that 1/8 in there. Don't think that 37 over 8 would be a very good idea to place in that particular position, because you have what we call a linkage error. Now, if by some chance you decided that you had this 37 value, and then in the next line you said, oh, this is an average value, maybe I should introduce that 1/8 times 37, that would be perfectly acceptable. It's sort of like a restart, sometimes we call that. And as long as you don't link things together that aren't correct, you're going to be perfectly in good shape. So Steve, did that cover, do you think that explains that idea fairly well?
That's excellent example of linkage. Sometimes we see linkage just with equal signs all the way across. So a student might get equal to 37. So they might write something like this. Sorry, you're on your screen. They might write equal 37 and then equal 1/8 times 37. That's the classic example of linkage. Tony, you brought up another good point about the approximation symbol. So that should indeed be an approximation symbol, but in general, we don't worry about those unless we're working with Taylor polynomials. So we don't generally take off for anything like that unless a student says that a function is equal to, say, its third degree Taylor polynomial. So good point.
Steve, real quick. Hey, Steve, because of time, can I jump to this last part here of a series? This is the part E from yesterday's test, just so students can see the answers. And we only have maybe 1 minute left, but I don't need you to talk about this problem. Students can see that this was a trickier problem. It was a geometric series, and they had to use some information from the table and then remember the sum of an infinite geometric series. But in general, can you maybe make a couple of quick remarks on, we do know there are a couple of convergence tests on this year's exam, like the alternating series test, p-series, geometric ratio test. Something like the alternating series has some conditions, right? And so we've been talking a lot about communication today, whether it's with symbols and notation, but also with words. There is an expectation, correct, that students would communicate if they're using a convergence test and how they know that it converges?
Absolutely. For example, if they're using the alternating series test, once again, similar to the mean value theorem that we talked about a minute or two ago, the student must write down, convey to you that the conditions are satisfied before invoking that test. That's correct.
Perfect. And man, Steve, I wish we had like 2 hours with you because you've got so many good ideas. I apologize that we're short on time, but we know that students have other AP exams and things to jump into. So if it's okay, Tony is going to do a quick T-shirt giveaway, and then we're going to let you pick our number.
Yes, Steve, could you pick a number between 1 and 259 and make it a positive integer, please?
137.
137, looking at our list, our first winner of the day, name is Hannah. Hannah, now there could be many of you named Hannah, so if you have a Twitter account that has Hannah in the name, just stand by for a message from us later on, and that will ensure that you're the winner, and we'll take care of some of the details about getting the shirt to both you and your teacher at a later time. Really super quickly, we want to tweet out our fantastic teachers that we want to appreciate, because it is Teacher Appreciation Week. So what better way to recognize teachers than here on AP Calculus BC Live. So we certainly want to shout out to AP BC teacher who not only teaches both, but has managed to do it while undergoing 2 surgeries. She does an amazing job. That's Mrs. Prowse, and she is from Beloit High School in Beloit, Wisconsin. So congratulations to you. And I literally just made this account for AP stuff. Shout out to Mrs. McCoy from Belton, Texas. McCoy is the greatest teacher ever because she's so patient and humble. She encourages us and everyone else to make mistakes and that they don't define us. Shout out to Mr. Wynn, my BC Calc teacher at Redland High School, for making lessons fun with his great taste in music and amazing quotes. Hopefully you can plug and chug this AP test for a 5 and flippity flop any bad scores. Bingo, bango, bongo, Mr. Wynn. Mr. Wynn, Redland High School, it's in Lewisberry, Pennsylvania. Mr. Wynn. Woo.
So, Steve, real quick, last 30 seconds.
Yes.
You've done these TI office hours, and I think you've got one coming up. We'll be posting information in our Dropbox with the problem so students can see it. But can you let us know when that was happening and how students might be able to attend, and is there a cost?
No cost at all. That's free, sponsored by Texas Instruments. It'll be tomorrow, Wednesday night at 7 p.m. Tom, Dick, and I are going to review 2 questions. We kind of think of them as remember those transition questions? So there's some AB material, but we're also focusing on BC material. We will make those questions available a little later today. I think, Brian, you've agreed, Tony, you've agreed to post those. We'll post them on the TI website. And Mark Corrali usually posts them on his site also. So we'd love to have you join us. It's done similar to this, I believe, Brian, on YouTube, but you can also post your questions. Wonderful. And look, Brian, if you'd like, we can come back later in the week here if you've got an extra 15 minutes and finish some of this off and answer questions. Your choice, okay?
I love it. We'll definitely look into that and we'll follow up with that. Steve, you are always gracious with all of your time and all your insights and wisdom.
Thanks. Great job. A lot of fun.
Always. Thank you, guys. It's been great. We're heading out because it's 10 o'clock. We got to get you out of here. So, Tony, final thoughts and outros.
I think that we pretty much summed it up all. Thank you very much, Steve Kokoska, for your insight. Thank you, Brian. Thank you, everyone, for joining us. We'll be back again tomorrow. And in the meantime, we want you to stay healthy, stay safe, and as always, keep learning.
AP Calc, yes, AP Calc. Welcome you to AP Calc, yes, AP